Well, first off, acknowledge I'm going to put more than just my name up there because I'm a part of a very productive and very wonderful research group. The other scientists in that group, including the wonderful dedicated technicians we have in that research group, really do provide a team that work with it that I find very exciting. The second thing I want to draw attention to is this is a session about nutrients, and you see I'm not even putting that word here in the title, and there's a reason for that, and I will come back to that by the time we get to the end. I started by asking myself a question and included it's really a question that came to me as a result of conversation with colleagues. It's not unlike, Joel, what you started off with. This thing is working. There we go. What do we know about cover crops today that we didn't already know 30 years ago? And I've looked at that same conference proceedings that Bill Hargrove put together, and there's a lot of great science that had been done and was in place 30 years ago. And and there have been some good things that have come to us since then. Joe, you brought some of those things to our attention here in your first presentation, and yet I kind of think that much of where we are today has not so much to do with added on science and understanding, but this renaissance that we're going through in terms of a return or to drawn attention to cover crops really comes as a result of our ability now to really, I'm not sure this is to look at soils and soils over the landscape and look at the soil function so much better today. We're integrating our sciences, the information of those sciences together, and as a part of that, we kind of recognize those different processes of soil function and the linkages of those things so much better today. And because of that, it automatically now turns our attention to cover crops. And it helps us to see cover crops perhaps in a little different light than what we have in the past. However, when we look out over the landscape and we look at different pictures of what we see, we oftentimes will see these kind of things, and I've seen a number of these slides in presentations earlier this morning. And if you look at those things relative to those soil functions, main soil functions, you're left with the conclusion that we have, in many cases, dysfunctional soils. They're not functioning well. And for that very reason, something needs to be done. Unfortunately, we as humans are quite a bit better at seeing things that we're not doing right than we are at seeing things that we do right. And so we've had to see a lot of scenarios like these images to kind of draw us to our attention that we've got to do something very differently. And so with that, in the past, we have tried to resolve these kind of issues with engineering solutions, very engineered type of products on the landscape to kind of deal with those kind of things. But in fact, if we look at that list of soil functions and the list of summary of things that we typically think of in terms of cover crops, we automatically see this direct linkage. And so I like to see cover crops as really it's an engineering solution perhaps, but it's a biological engineering approach to getting at those same things that we need to address. So this is very much the message we've been hearing over and over again this morning, and it's where I come from with this research group in Columbia, Missouri, and it's the Cropping Systems and Water Quality Research Group. And one of the things that ARS is very good at is kind of committing themselves to long-term research. And we've been doing some research in the Salt River Basin, which is the northeast corner of the state of Missouri. It's the watersheds that flow into Mark Twain Reservoir in that portion of the country. Watershed monitoring, but also research on individual fields and plots in this area. So as a part of this, we got into looking at cover crops because of what we saw relative to these soils in this area. The soils in this area are referred to as clay pan soils. It's Major Land Resource Area 113. They're very difficult soils. They're very problematic soils. They shed water very, very easily. And did some work on both large watersheds as well as field-sized watersheds. This is one of those fields, and this is an aerial photo in the early spring, and you can see that it's not really, it drains in a very strange way, and that's just kind of the nature of these clay pan soils. So on this field, had done some very intensive evaluation that started in the early 1990s. The field was being managed in a corn soybean mulch till, very typical to this area of the world. As a part of that evaluation, we looked at groundwater quality, we looked at surface water quality, we characterized the soils with different manual type sensing as well as sampling, and then laboratory work as well as on-the-go sensor work that we've been doing. There's soil quality evaluation that we have done. We've started, it's one of the first fields that we really regressively started in the yield mapping. Our first yield maps off this field were in 1992. And then started developing the spatial relationships of many of those things you see on this slide now. So this field became a case study field for us to be able to understand a lot of things that are happening on other clay pan soil fields in this region. With that, we saw what we were able to say is that you looked at that field, it was one of these fields that we would say is pretty dysfunctional. It's just, you couldn't take those, you couldn't go out there very many days during the year and say, this really looks like a good, healthy field. There were times when the runoff off this field were a whole lot more. This is a 90-acre field, okay? More runoff this field than many streams that I fished out in I grew up out west, and it's much smaller streams than this that was coming off of this field. So this field it gets very, very willing to shed when you get rainfall events. So we knew that there needed to be something done differently. One of the things that drew our attention to the dysfunctionality of the soil was really looking at the historic erosion that had taken place on this field. And again, it's very typical of other fields in this region of the country. And one of those sensor systems that we use to do that is soil electrical conductivity. Here's a photo of several different types of soil electrical conductivity. And with that, we're able to map at a very, very high resolution depth to the BT horizon. So where you see a dark green there, it's still deep. Actually, it's an area where you've got alluviation that's come down slope into an area where it channels off the field, to the yellow being very shallow. And what we have when we look at this is we find, well, first off, we additionally got some numbers from some fields or some areas near this field that had not ever been in cultivation. We were able to create a model that regenerated a representation of what the topsoil depth of that field was prior to man coming in and starting to cultivate it. So you have on the one side, I don't know where the pointer is on this thing. Is there a pointer? Maybe not. Anyway, on the one side you have, this would be like the pre-cultivation. This is the way it is today. You take it's moving on its own on me now. I'm not sure what to do. I didn't think I touched anything. Okay. This will be interesting if it starts. I'll have to run to keep up. Anyway, so this is what it was before cultivation. This it is now. The difference of those two maps give us the topsoil loss. It's been on average more than 7 inches of topsoil, but over 30% of the field has had more than 10 inches of lost topsoil since cultivation. So in 120 years, more than 10 inches off at least a third of that field. And there are areas of that field that have had 16 inches of topsoil lost. So this is a degraded field. This is a field in need of CRP. This field is really tough. But again, it's not unlike a lot of other fields in that area. That's what I was doing, and that was, okay. So what's been the impact of this on productivity? This is where we merge the EC-generated topsoil depth maps, and we look at also the relationship with the yield maps. And what we have, and this is a 10-year yield map, each of 10 years, and we transform that yield map into a profitability map. So we're taking the input costs, herbicide, seed, fertilizer, all those things, land, labor, everything, and then you're taking your yield map and transforming that into what you got at the elevator. You're merging those together for each individual year and then combining across 10 years, and you get an all, for a decade, what the profitability was on that field. Where it is brown, over that 10-year period, you didn't make any money. Okay, you lost. So 60% of that field, you made a little bit of money, but 40% of that field, you didn't make any money on that field. This particular analysis brought us to an awareness that, this is really a field that's a candidate field that needs to have something very differently done to it. And so from there, we started looking at different things, and on some side research next to this field, we had been introduced some cover crops, and we felt like that cover crops in conjunction with no-till was the way to proceed forward. And so that's what we did. So from 2004 to the present, it has had on the north end of the field, we took it out of corn grain production and went to wheat soybean rotation. And on the south end of the field, it's in a soybean corn rotation, but it uses no-till over the whole field and it uses cover crops. So the combination of no-till and cover crops, I think, is the key to the changes we've seen on this field. So this is kind of like, in your magazine, it's a weight loss program, the before and after picture. Okay, so we're going to have some before and after little pictures here. This is what it was before, now it's after, and to look at what kind of changes have taken place then. What has been the impact of this decade worth of no-till and cover crops? Okay, so this is the before. So this is looking at the sediment loss in tons per acre. The blue is the field, and the red is actually the larger watershed, a 28 square mile watershed that this field is within. Okay, so you can see from this, the first 12 years here, the amount of loss on the field was about just a little over 2 tons per acre annually. On the watershed, it's been about 1/2 ton per acre. So the amount of sediment that was generated off of the field was considerably higher than the larger watershed that field was within. Now 350% higher than the watershed. Okay, the after. Okay, since then, with the cover crops and the no-till system, we are less than 1/2 ton per acre per year of sediment loss. And actually, the majority of that came in 1 year when we were still we needed to do a little bit of earthwork, and we actually stirred things up more than we wanted to. And this is at a time period where we've had some of those intense rainfalls, and in actuality, the loss at the watershed has been considerably higher than what it was the previous 10 years. So, the before and the after, huge difference. I mean, hydrologically, this field doesn't even behave the same way that it did when we had it under previous management. And the no-till with the cover crops is really that management change that has allowed us to really change this very quickly. Why is this important? And this is the message that when I share with, visit with farmer groups, that I want to put into here and help them to understand, and that is this. Used to be, we say, reduce erosion to 2T, 2 tons per acre. Well, 2T is not, I don't think, based upon what I see in the literature now, is an overestimation of the rate at which soils form. For these soils, the rate of soil formation is somewhere between 1/2 and 1 ton per acre per year. Okay? So you can see that where we were before, we were still degrading the soil. Where we are today is we're below that. So we're really, in essence, we are down now below, the erosion rate is below the formation rate, so we're actually gaining some soil back. And that's an important message for farmers to see. If you want to make some changes and think of sustainability, you've got to have something that's radically going to change the way you manage these type of fields. Okay, when do cover crops reduce the runoff? I'm not going to go into how we did this. The important thing is to recognize the red line here on this, and we're looking at the 12 months of the calendar year. The red line represents the first period of time, the first 12 years. The blue line represents the field that we've had in the cover crops and the no-till. And the real difference is that we have on the order of a 25 to 30% reduction in the total runoff, and it's happening during the most vulnerable part of the year, which is the first 6 months of the year. That's when we see the significant difference between the previous management system and the current management system with the cover crops and no-till. I'm going to switch gears just a little bit and talk about soil quality, and there's a lot of discussion about soil health, soil quality. Okay, and there's a lot of different ways to look at it, but I'm a numbers guy, and I want numbers. And I hope that we can continue to be advocates for numbers in terms of how we create soil management or come up with soil quality. And Dr. Kramer and Dr. VM in our research group has done some neat stuff with regards to the soil, using this soil management assessment framework, which is a very flexible system of being able to take the numbers that we've used in the past to look at soil quality or soil parameters and to kind of bring those together in an index way. And so there's a score put together relative to the physical properties, the biological properties, chemical properties, and the nutrient properties, and those kind of come together. Well, in their survey, they did a whole bunch of different fields in that same area as this field I was talking about. And it's kind of hard to see that from where you're at, but so I'm going to kind of help you out. But here are the fields that were in grass and pasture. Here's the fields that were in grain plus the cover crop. Here's the fields that are in the no-till with grain. And here are the fields that are mulch-till and grain. And the number of years that they were in those systems are represented by the numbers that you see on the bottom here. So you can see really a natural progression of lost soil health or soil quality based upon this index. And you can see that really with the grain and the cover crop, you're getting up there and kind of almost overlapping with the same type of numbers you get off of fields that are in grass and pasture. If you look at these different scores independently instead of as a total, like I was showing on the previous slide, that's the physical, there's the biological, there's the chemical, and there's the nutrient. And you can see there's not nearly as much difference between the chemical and the nutrient as there is with the biological and the physical. That's where you see the differences on this particular soil. So these are the properties that you're having the real impact on for this soil and where you're going to make a difference in terms of that soil health. So using that same framework then to come back to our case study field and the SMATH total scores that we had for the, and for the first period of this field assessment, we would have a SMATH score of about 76. A dysfunctional soil, that's not very good. That's a soil that has a difficult time growing grain crop. After just the 10 years that we've had that in there, it's up to about 88 now using this index. So we've increased the soil quality index by about 1 per year over that 10-year period, which leads me now to the question of, can we do something differently than what we started off with? Because this profitability map, the reason why it's negative up there is because corn production was what brought it down below a profit level. The soybean has done okay, but the corn was really what created the brown on this graph. So now I'm asking myself, have we built the health back into that soil after 10 years to where we can consider corn coming back into this soil that was previously degraded to the point we had to take it out? So that's one of the storylines I think it's important to kind of deliver, is that, you know, it's not just, it's building some health, it's building sustainability, and it may allow us to go back and use some fields that previously were degraded and we had to go out of grain crop production with certain grain crops, and now we can go back into them with that. So that's my final slide here, and I said I would come back to the nutrient part of this, and that is, if you look at the University of Missouri Soil Fertility Recommendation book, it doesn't use the word cover crop in it at all. And most states are probably that way. And that's because these recommendations for soil fertilizer recommendations are often built upon plot work where soil function was not an issue. And so if it's not an issue, maybe they work fine. But where you have problem fields like this, and this is not a rare event, a rare field. There's a lot of fields out there. That the nutrient management decisions need to be made in light of how well it's functioning with these other processes of how we see soil health. And that's the take home I would hope that you could get from my message today, and the long-term research is supportive of that kind of thinking that we need to have. Thanks.